lecture yesterday, you will have heard everything I've got written down in it. It's stolen from the website. So Andrew works at the intersection of mathematics and sometimes surprising aspects of the world to which it can be applied. Falling paper, breaking spaghetti. I've seen him break spaghetti. It's dangerous. Or strategic games. Maybe not so dangerous with the games. Received his PhD from Princeton in physics. Do we really allow physicists in this building? From Princeton in 1994, and did a postdoc at the Institut Nonlinéaire de Nice and the University of Pittsburgh. In 1998, joined Penn State in mathematics, and then later got positions in the Department of Materials Science and Engineering and in the Huck Institutes of the Life Sciences. So a pretty varied background. And was recipient of the Sloan Fellowship and a Curie Award. Andrews had visiting positions at ESPCI. I'm not sure what that is.
Physique et chimie. That's the
okay.
sort of like it's the technical the special school for the study of physics and chemistry of the city of Paris.
Oh, okay.
ESPCI.
Thank you. That's Paris in France, it says here. 2004, and at Harvard, at the University of Maryland, at the University of Paris 7, and at the National Cancer Institute recently in Maryland. And today Andrew will talk about Do Your Fair Share, Evolutionary Games and the Tragedy of the Commons.
Thank you very much, Michael, and thank you very much for inviting me to give not one but two talks. I look forward to telling you about some of the recent work that we've been doing. I hope you can hear me okay without good microphones or anything like that. And I'm happy to have a more flat room than the sort of frighteningly angled room that we were in yesterday, because I like to move around. So I want to tell you about some things we've been doing in game theory. And so I just want to start, since it's a colloquium, just to sort of orient things. E pluribus unum. This is on the dollar bill, and it was the motto of the United States up until the mid-50s. You mentioned yesterday that the mid-50s, if it says anything to you in American history, it's the Cold War. So from many as one. So it's sort of a civic-minded, public-minded motto that we had here in the U.S. And so sort of what I want to talk about, this is the Oath of the Horatii, is an event that happened in ancient Rome in which three brothers all volunteered to defend the city. So the thing I'm starting with here is this civic-mindedness. Do your fair share, contributing to sort of the common good or the greater good or the public good. David, if you know French history and you recognize these years, this is around the time of the French Revolution. So it was around the time when why should you risk your life and march against the king, to improve society. So I want to talk about this in the context of game theory and of economics and of biology, because often evolutionary biology or economics is built on assumptions of selfish motives. Okay, so I need to survive because I need to have children to get my genes further along, and anything that I do that makes it more likely for me to pass on my genes is the sort of behavior that will be encouraged by evolution. Right? Because people who waste their time doing other things, they don't get as far as I do, and their genes don't propagate as far. I mean, that's a very mathematician's version of summarizing sort of some of the arguments in evolutionary biology. Economics, you can do the same thing. So how do you explain the fact that we often see behaviors like this and the choices like this made in biology or in society, and what's the math involved? Okay, so that's what I'm going to talk about today. And I'm going to talk about it in terms of a particular game called the public goods game, which is, well, I'll tell you. And then and I'll sort of summarize the results of Public Goods 101, which is always better to cheat. It's the selfish thing to do. And then I'll go through two, or actually this is two different subjects here about migration, and then also about fast-moving cheaters that lead to the fact that, you know, maybe it's not always better to cheat, or maybe cheaters and non-cheaters can coexist together. And then I'll talk about some other multiple games, and that's what I'll present to you. The common theme here is that by making new developments in the model, you can try to explain. I mean, just basically we expand the model. Okay, so tragedy of the commons. If you've ever heard this phrase, it was first presented by a minister in England, Lloyd, and then later. So Lloyd, let me describe Lloyd's original description of the tragedy of the commons. This was around the time when cities like Boston, for example, would have a commons where you could graze your animals. And the commons was owned by everyone. So imagine that your pigs are out grazing in the town square. I don't know if you have one of those in Raleigh. And I have my pigs out there as well. So what if I purchase one more pig and send the pig out to graze further? Well, that benefits me because I have one more pig, but it reduces the amount of lawn that's available to everyone's pig. So we all sort of share the cost because everyone's pig has a little bit less to eat, whereas I benefit from the purchase of the pig and whatever I decide to do with the pig. Later, Hardin in the 60s talked about this in terms of population growth. The basic idea is, I like to describe in academic circles in terms of the public or common microwave. Graduate students in the room, there's right. So everyone, you know, I'm sure your department, like my department, has a publicly available microwave. If everyone who used the microwave cleaned the microwave would be clean. Everybody would be happy, right? We all know that that's true. But if one person uses it but doesn't clean it, they're still using a pretty clean microwave, and everybody else is cleaning it. So, you know, we've got 30 people sharing the microwave, 29 people are cleaning it. That's great. You know, it still works, right? It's very tempting to be that one person. You know, I'm not going to. So, but the problem is everyone feels that way. So no one cleans the microwave. I think I've said this so many times in so many talks, I'm going to start taking photos. Or maybe I can take a photo of your microwave before I leave. Because our microwave at Penn State is filthy. Absolutely. Why should you invest your individual effort towards a publicly shared good? Different way of saying it, why should anyone contribute to an effort if you still have the option to enjoy the results without contributing? It's a public good. So it's a different version of this lawn that all animals have access to. Okay. Now, there are some biological examples of this, and the one I'm going to talk about today has to do with a really interesting species of ant, which occurs in Japan. It's a queenless ant. These ants are reproduced by parthenogenesis, something I'd never heard of until I started looking into it. There's no queen in the nest. Every worker lays eggs, and those eggs are fertile when laid. There's no sex going on in this colony. Every worker is basically cloning herself when she lays eggs. Okay? So, for a mathematician, this is just a really nice system. Because whatever genetics each individual has, they pass directly on to their offspring. You know, it's like they're bacteria, but they're not bacteria, they're these ants. So, within this species, for example, Pristomyrmex punctatus is one of them, there is a cheater genotype. Oh, I should say, every worker is a queen, but she's also a worker, so the eggs get cleaned, they get put in the room where the eggs are, and the nest gets cleaned, and all sorts of things happen that are normal to an ant nest. And the younger ones go out and forage for food, and they take care of things, and the older ones, I think, are the ones that stay more in the nest. But there's trouble, because this genotype, the cheater genotype, they lay eggs, that's all they do. Their eggs get taken care of and raised by everybody else. It's sort of like the cuckoo in the bird kingdom. It's not a kingdom, but among birds. So Dobata and Tsuji, and this is in a PNAS article, they actually went out and collected these ants. You can tell the difference between the cheater genotype and the regular genotype, and they made different proportions. They did laboratory experiments, and here's a laboratory experiment that's something like 80, 90% worker, regular worker, cooperator, contributor, and this one is 80 or 90% cheater. So it's filthy, the nest is filthy, the eggs are rotting, nothing's going on, and the nest is sort of doomed because it's mainly freeloaders, but there's nobody cleaning the microwave up. Okay. So the public goods game itself, in terms of game theory, was posed by Kegel and Roth, and it illustrates this puzzle sort of in an economics/mathematical way. So one player produces a good, and producing that good costs something, C, and then there's a return rate, which is a rate, so the amount that comes back from producing it is R times C. So if C, unless R is greater than 1, one individual would never do that. So we're going to talk about the situation in which R is greater than 1. If you have n such players, again, this is a public good, so it's shared. Each individual who contributes pays cost C, and each individual who contributes receives in return RC over n, population of size n. So no matter, well, so each individual, if there's only one of them. So the effective rate of return is n, R over n, excuse me. So if you have U total members who are contributing, then each individual receives RCU over n. And so the question is, what do they do? To clarify this, let me give you the thought experiment that Kegel and Roth used. Economists, so we have a stack of bills here. We're going to do this with money. Okay? So I'm going to choose 5 of you in the audience. I'll give each of you $100. Okay? That's T equals 0. Then I collect from you voluntarily, you of you, whoever wants to volunteer, I collect some amount of money. Your decision. How much do you want to give me? I just gave you $100. How much do you want to give me? And I tell you in advance that however much I collect, I'm going to double. And then I'm going to return it to all of you. All 5. Okay, so clearly, if all of you contribute, everybody gets 200, right? I gave out 100. You give me 100. Back to 500. I double it, that's 1,000, and I divide it by 5, 200. That's really good. But if only 4 of you contribute, then let's say you all contribute. Obviously, you can give me however much you want, but let's say 4 of you give me 100, the other person keeps their 100. So the contributors, it would be 4 times 100. I still have to divide by 5, so you only get 160 back. You're still doing okay. Not as well as you would have done if that 5th person contributed. Whereas the freeloader or the cheater gets 260 instead of 200. Nice. Why wouldn't you do that, right? Etc. Right? Imagine this situation in which one person contributes. They get $40. Everybody else gets $140. So I mean, you're not doing as well. Even if you're freeloading, you're not doing as well. But this is the problem. Okay, this is the public goods dilemma. It's obviously better not to contribute. I do want to make this point about the language. It's just in the literature. It's called cheating, but it's not actually cheating. You're following the rules. You're not breaking the rules. So technically, you're just freeloading. But in the literature, it's called cheating. So, so now let's go through a little bit more in terms of the population for a public goods game. So let's say that there are 2 populations now among a total of n individuals. The producers have this as their payoff per individual, and I'm just going to call that the fitness, because I'm starting to move towards a population biology interpretation, whereas the freeloaders, who would be the ones who didn't contribute, this is their individual fitness. So you can see it right here. Your fitness is always higher if you cheat or if you freeload. That's the tragedy of the commons. It's much better for an ant to just walk around laying eggs. Energy is not taken up by doing anything else. They're just reproducing. So their fitness, in the biological sense, it's higher. Okay? So this is the choice. Should you contribute or not? Do you want to be one of these? Here's the public good that comes down to everyone, or do you want to be one of these? All right, so I'm talking about fitness, so I have to say a little bit about fitness. As a mathematician, I love the idea of fitness because it, Harden, this is a quote from Harden, it commensurates the incommensurables. You know, it just sums up everything I've done as a biological organism and just says, my fitness is high, or my fitness is not so high. You know, I'm a dinosaur, I'm big, my fitness is really high. When I wake up and it's snowing, my fitness is no longer high because the world has changed. Right? I'm a lizard. So somehow the fitness sort of balances everything out. Biologists, not all biologists like the concept of fitness because it puts all these things together that are different. And how do you do that? That's some sort of method. It's very attractive. Right? So it's some sort of norm. So there is a world of sort of evolutionary dynamics in biology in which you just say the proportion of the population, say species I, that's contributing, that has some properties, is growing or has an effective birth or death rate that's given by the difference in fitness. This is the fitness of species I. This F bar is the average fitness over all the species with which it's competing. So this replicator equation sort of summarizes the approach or the idea that the survival of the fittest, which Darwin never said, but basically which Darwin implied, which is that the ones who are fitter are doing better. So this differential equation is the basis of what we're going to use. So here it is. This is for the public goods game using the replicator approach. And again, it's the same thing as before. If you go through the differential equation version, it's no surprise that the one with the higher fitness wins. And so the two fixed points are either, the only way to get everyone to contribute is to start with no cheaters. Because this is a reproduction model. So if v equals 0 initially, there are no v ever, there's no cheaters. Or the only other fixed point would be extinction, basically. U equals 0. So there's no steady state coexistence solutions for this sort of simplest approach. So cheaters always win, but it's not really winning. Because if u is 0, then okay. So this model is sort of not explaining what's seen if we see coexistence. Okay, so people have taken different approaches to this mathematically. So the idea of Howard, Holmes, and Dobley was to instead of looking at the entire population, let's look at the game played in a smaller group. Okay, so let's assume that this individual is playing with this group and is just looking at the red ones being the contributors and the green ones being the cheaters. You're going to look at whether or not you should choose to contribute or not in this smaller group. Okay, so it sees just the payoff from this smaller group. So the payoff difference is only, it's not RC over N, it's RC over S. So this averaging, but of course the group size is to some extent random, so you sort of want to average over all different group sizes. So this approach, sort of synergistic, what they call a synergistic approach, is you need to sort of take the weighted sum over all possible groups you could be in as you're thinking about it. Okay, so if you take that sum, you just get, it's just basically a geometric series, so you can see here the size of size n, over all the possible sizes you could have. And in this case, you get this modification to the fitness. Okay, so with this approach, you can get steady state coexistence points for cooperators and cheaters, which just corresponds to the fact that under certain conditions, certain initial conditions, it doesn't look so bad to cooperate because you're not looking at the entire population, you're looking at a smaller group. Okay, but of course, it still depends on the parameters. Okay, so that was the approach that was taken before. The approach that we looked at had to do with space, because another way to solve the problem of the dirty microwave is to go to somewhere where there's either more people are doing the cleaning, or maybe there's just a clean microwave. Okay, so what effect would that have if we allow for spatial degrees of freedom? Everything we've been talking about up to now is just all of these things together competing, but I've been ignoring space. I've just been using ODEs.
Can I just ask a quick
Oh,
question
yeah.
to clarify? In that system that you had a WN and a WN minus 1.
Yeah.
What was the notation?
Yes, I'm sorry. I skipped over that, but so there's a density effect in here. U and V are the proportions, but we're sort of looking at it's basically a crowding effect. So W is a parameter which represents how close we are to totally populated. So this I forgot to mention this. This is just a free parameter. I'm sorry. This is just a function of U and V. So it's a little. I'm following their notation, which this down here 1 minus. Why am I dividing by 1 minus W? This is just U plus V. 1 minus W is U plus V, so I should just swap that. This is just U plus V, this is U plus V. So this is just RCU divided by the number of cooperators and cheaters. Oh, and I also said, at some point I've mixed my notation here because I previously was using capital N as the size of the population. But actually, I LaTeX these from their paper, and this is their N. This is S. This really should be capital S.
Okay.
Sorry. That's to anticipate your next question.
Right.
This should be capital S.
No wonder I was confused.
So there's no delays in that system.
There are no.
There's not like delayed consequences.
There are no delayed. That's correct. There's no delayed consequences. That's a good point. So at any given moment. The fitness is a function of the number of people who are contributing and the number of individuals who are freeloading. There's no time. Yeah, that's an interesting point. But to some extent, space you begin to add dependence on other things. Time delay is that's an interesting thing. I haven't thought about that. Time delay in the good, in the arrival of the good or something, the public good. Or something like that. That's an interesting. I'll say something about that later. Okay, so space. So there's a tradition of looking at spatial games. This is a picture of Martin Novak. I think it was his. Actually, I don't know if it was his thesis work, but this work with Bob May. This is just individual players sitting on a square grid and playing Prisoner's Dilemma against each other. Prisoner's Dilemma. We talked about it yesterday, but Prisoner's Dilemma is this game in which it's always better to turn the other person in. You both turn each other in, and you don't do as well as if you had both not turned each other in. But when you add space, you can get more complicated things. This is an example of the patterns for that. In nearest neighbor coupling, there's other ways to couple things spatially. And going back to the Fisher equation, or in terms of evolutionary games, Vickers, you can just take this differential equation, this ODE I was just talking about, and throw a Laplacian on it. So basically it's like a reaction fusion equation, but it's replicator. So replicator diffusion, PDE. So we did that, but we did something else as well. We added a fitness gradient. So a few of the models, so this is one of the three results that I'll be telling you about. So in this context, I want to introduce that in addition to random motion, this is a player, and let's say cooperators and cheaters in different rooms. This player could wander randomly down the hall and play a game in one of these rooms. Or this player could also sense that its fitness would be higher if it went this way. So this is you see here the fitness gradient. It's a fitness gradient. But when my student and I thought of that, we thought it was a new idea. In fact, of course, that is in no way a new idea. I wasn't reading the ecology literature. That's why I didn't find it. But Shigesada et al. Basically came up with this idea in 1979. And a lot of people have used it, including almost an identical model to what I just showed you by Chris Cosner from Miami in 2005. So a lot of people have. It's not. I should have realized, right? It's just connected to something well known in ecology, the ideal free distribution, that a population will be higher in places where there are more resources, and will be lower, out in the desert where there are not as many resources. So a lot of people have looked at non-diffusive fluxes in replicator-like settings. So that's what we did that as well. We did it for the public goods game, but just with diffusion was already done by Christoph Howard and co-workers, and so they did a lot of pattern formation studies. So this is from the PNAS. Basically, they see this is extinction over here, and this is just sort of healthy cooperation. They see a whole variety of things, including turning-like patterns and other dynamic states here. And stripes as well. So you could think of a steady-state stripe pattern as being a bunch of cooperators here surrounded by sort of cheaters. The populations sort of go down. It's a pattern-forming system. Excuse me. So what we did was take their system. This was the first project, or second project for my PhD student, Russell Forrest. And then we added these extra terms, just fitness gradient flux. Okay, so I'll just show you a few selected highlights from that. This is one dimension, so this is space and time. As we add fitness gradient flux, we actually extend the region of Turing patterns. So we actually, I don't have a parameter plot yet, but this region here where Turing patterns turn into extinction, it extends. It's not really surprising. This is an example of a 1D simulation because they now they don't just wander randomly; they can actually find each other. So they're looking for high fitness. And also the speed. This is sort of a group of cooperators spreading out. They actually move faster as you increase the parameter for fitness gradient flux. And this is a case where they expanded. So I just wanted to show you that extinction is still possible. So this is again a one-dimensional system. This is time, and these are the cooperators on this side. These are the cheaters on this side. So the cheaters are following the cooperators around. Cooperators are trying to get to a place where they can just have clean microwaves, and the cheaters are following them, also wanting clean microwaves, but not cleaning them. Right? It's the public goods game. So what happens in this particular pattern is you see they actually, at each of these points, in local in space, extinction. Extinction, extinction. So, and then it's blue forever after. They all die. Okay, so I think I've said all of these things, so and I'm going to skip over the dynamic states until the end, except just to show you, we see dynamic states as well that sort of fill all space, and the dynamics are interesting. This, I guess, is just to show, I could have moved this earlier, but in a stationary state, you can take a slice along this line. Here again are the sort of Turing, it's very much a Turing pattern situation. You've got the people who clean things and surrounded by the inhibitors that wants to follow them. And they reach some sort of steady. Okay, so I'll skip these other dynamics. I'll skip this as well. Come back to that if you'd like. And talk about the second area, which is to now look at this on networks. Because we were interested, well, we started out by being interested in this system and thinking about fitness gradient flux. But then we were also thinking about the ant system. Right? And the fact that, what happens to these nests when you've got higher fitness freeloading ant running around laying eggs. That means that slowly over time, the nest is becoming more and more freeloader rich. This is an actual, not in the laboratory, but in the wild, what happens. And I was actually in contact with Dobata. So these are the two ants, just to remind you. Punctatus is the one they worked with, but they had a few papers on Christobermex pungens. I actually was in contact with the Japanese group because I suggested that they look at some networks in the lab, and so we were talking about that. Let's see, I think I told you everything here. Here's a picture. The cheaters are slightly bigger. And we'd like to say that's because they're more fit. Of course, that's not. There's no reason to. It could just as well be the other way, right? But they are slightly larger, so they can keep track of which ones are the cheaters and count the population. In fact, so here's some. Suji was the one I was emailing. Here's some of their data from the PNAS. Depending on the initial proportion of cheaters, what's the proportion of surviving ants after some certain amount of time? The more cheaters you load it with, the further down it goes. And these are two different conditions. paper, but the point here is just looking at, the points are the data. The curve is just meant to go through the data. The line is meant to misguide the eyes, as they say, to show you that in each case there's this sort of trend towards fewer surviving ants as you increase the proportion of cheaters initially. So we want to model this. So, so what we've done is we've taken the public goods logistic model. So here it is as an ODE. So this would be the fitness here. And we've added a crowding term. So it's logistic growth. Here's the death rates in the two nests. For the two populations. This is the contributors and the freeloaders. And here again is their fitness. Here's the fitness of the public goods game. See minus C, and there's no minus C here. At the end, I'll come back to this epsilon. So this is the dynamics within one nest, but then we're going to look at networks. Okay, so it's not going to be a PDE this time. It's going to be coupled ODEs, and the coupling functions are going to be these sort of reversing heaviside functions, which are just the fitness difference. I guess I didn't write them down. These are just the fitness difference between the two nests. Not always in such a way that the flux is always towards the higher fitness. So there's a flux proportional to beta that always goes in the direction of the higher fitness. And this is the dynamics in nest 1. This is the dynamics in nest 2. So if I look at the single nest dynamics, there are two fixed points. There's sort of there is a coexistence point, and then there's an extinction point. These are different trajectories for that. If I look at a network of two nests, and we see a variety of dynamics. I think I should skip to this first. So the difference between this and everything I told you previously is they're able to move. Okay? They're not diffusing. They are moving to the nest where the fitness is higher for them. Okay? So there is a region here of nest collapse. So this would sort of be the classic ODE result. The nest collapses. And this is the mobility coefficient for the cooperators. This is the mobility coefficient for the cheaters. But there's a threshold here where you see oscillations, and then there's a threshold over here where you have stable coexistence. So let's see. So this one is stable coexistence. So this is nest 1 and this is nest 1 and 2. The cooperators, this is nest 1 and 2, the cheaters. So they reach some sort of stable. Here are the oscillation cases, and then here's a case where one of the nests goes extinct, and the other nest goes into so this is the other nest going into a coexisting state. So you get different dynamics, and this is the sort of phase plane of those dynamics for two nests. And this is work with my postdoc. Okay, if you put in 4 nests, this is coupled all to all, then the dynamics are different. There's different transitions, and there's a wider variety of behavior. Okay, but
What was the topology of the network?
This one is that's what I'm trying to remember right now. I think this is in the case of I think this is all to all. All of them are connected. That's a small.
No. It's a smart board.
What's this one?
Yeah, you have to be smarter.
Or there's
I have to be
smart,
smart enough to write on.
there's smart markers too. But
Right, so this is just. We did a lot of different configurations. I think it's this one. The surprise that we saw for the n equals 2, the n equals 2 nest, it's also there for the n equals 4 case, and obviously there's a topology dependence, but the surprise is that is the way in which this line, so let's start here. Here we did it this way, but if you start here, you see that you can go from collapse, let's set beta u equal to 1. You can go from nest collapse to stable coexistence by making the cheaters move faster. That's surprising. Okay, so these are just different cases to show that you can have oscillations. This is just sort of a zoology of all the different things we see. There is a complication in the, there's a lot of complexity when you start to have collapse, because if you have depending on the topology of the network, when one of the nests collapses and everybody dies, the topology of the network changes. There's sort of an evolution of the topology as well. Oops, I haven't back into that yet. So there's a lot of complexity here, and we're still, in terms of a sort of a topological theory of the networks, we're still working on that. But we've definitely seen that coexistence is possible in these networks in the case, well, among other things, in the limit that the cheaters are moving faster. So now, why is that? Well, it's clear from looking at the dynamics of this thing that they will, if the cheaters move faster, it sort of makes both nests not very nice. And what drives migration of the cooperators is to move to a nest that's nice and clean and doesn't have many cheaters in it. And this tends to empty the other nest, leading to a crash of the population of the cheaters. And so depending on the dynamics, this can lead to a crash of both populations in the nest. But when all nests are sort of equally bad, this is our understanding of why coexistence occurs for fast cheater dynamics, cheater migration. Because when all nests are this region here of stable coexistence, it just sort of evens out. Stability comes when the fitnesses are equal between the nests, because the populations don't change. So that's an interpretation of what we're seeing, is that the migration is stopping, or the reason that the migration stops when beta, in the limit of beta v being large, is because the cheaters sort of get there first, and it reduces the flux of the other cooperators. Okay, that's just an interpretation. Whether we can make a proof out of that's also important.
What are you using to simulate?
What are we using to simulate? This is being done the numerical simulations are being done in MATLAB.
But are you using integrators that introduce damping or don't damp? Or?
We are no, I think they're not. There's no explicit damping going on. But in the case of this, Glenn is a student of Bart Ehrmantraut, and so we're using XPP to look at the transitions here. So these lines are coming from XPP. We're doing a sort of a bifurcation analysis of the system, at least for inputs. So I just wanted to show you this one plot. So this is another aspect of the model, which is in the case where you have there's a certain regime of parameter space where you have coexistence, but only in one of the two nests. So one nest collapses, the other nest doesn't. So which nest collapses of the two? It depends on among other things, on the initial conditions. So here we're looking at the initial. You fix the initial conditions of the cheaters to be equal in the two nests, and you vary the initial conditions of the cooperators in the two nests. And so as a function of this, and so the red corresponds to nest 1 being the surviving nest, and the blue corresponds to nest 2. So this is sort of complicated looking, sort of sensitive basin of attraction for the, let's say, left nest versus right nest surviving. And of course it's symmetric, it doesn't matter. There's no other difference between the nests. The nests are identical in every other way. We don't understand this. This is something we sort of noticed in the simulation, and then we plotted it out as a function just of these initial conditions. Okay. Excuse me. So just to summarize some of the things we learned in this model so far, that fast cheaters stabilize coexistence, because we can see numerically that the fitness gradients or the fitness differences between the two nests are going down. I didn't show you a lot of these results, but depending, we can do a lot of different nests, 4, 6, 8, or whatever topology we want, and then we can see a more complicated phase diagram of collapsing and also disconnecting. Whether or not this corresponds to migrations and nest dynamics in nature, that's a different question. There's not a lot of data on that, at least what I've understood from the field work that's been done. And then we did see this sort of unusual initial condition, or dependence on initial condition, in the case of two nests. Okay, so that's part 2. Now one more part on public goods games. So I want to go back to the original situation. Okay, so you have two populations, and one contributes to the public good, both share in the public good. Actually, it's one person, several people made this comment to me when I described freeloaders, who just take from society and don't give anything back. Someone once commented to me, it sounds like a mathematician. You're enjoying lots of things, and what are you giving back to society? Or an artist, right? That's obviously a sort of a sarcastic comment. But it did start me to think about the fact that in an organized society, of course we have money. I educate people's children in the State College, Pennsylvania, and there are other people who make coffee for me, or make bagels for me, right? And we exchange money. But I could just as easily, they could just pay me for their tuition in bagels or coffee, right? So I started to think about the fact that in an organized society, there's a sort of division of labor, and some people, you could conceive of it as freeloading, but it would be, there's some sort of good that's exchanged. So we started thinking about creating a model in which there was more than one public good. So if, let's say, you had two public goods, okay, so, and each population contributes to one of them, and each population benefits without contributing from the other one. So mathematically, if you do that, I would call this compensation, right? Not compensation in terms of being paid, but in terms of something else is compensating for the things that are being sort of freeloaded away from you. The compensation is perfect. There's no dynamics. The equations, as we've written them, are such that these things cancel and nothing ever changes. It's sort of a perfect two-good system, but it's not very interesting in terms of mathematical model. So we move to three goods. Now we have this sort of situation in which, and again, this is another network, each population participates in one of three public goods games, cleaning the microwave and whatever else you want to think of. And in each case, you contribute to one, you receive goods from the other, and there's a third game which you are totally uninvolved in. Okay, so three goods, three games. There'd be other ways to connect this, but this is the way we looked at it. So if we use the fitness functions from before, then everyone is paying a cost for one of the games. Everyone is receiving benefit from one of the games that they contribute to, and one of the games they don't contribute to. So it's just a public goods game between three interlocking populations, all playing freeloading and contributing. Okay, so there's 4 fixed points to this dynamic. The 3 are the standard 3 from the other, sort of coming from the standard public goods game. In the end, everyone else goes extinct except for one. Except this time, everyone is sort of contributing to one game. So it's not extinction, it's just monoculture. Right? So the 3 pure strategies, that corresponds to everyone contributing, the other 2 are 0. And then there's one coexistence interior state. And if I assume that all the returns are the same, to some extent well, you see it only depends on the returns. The interior point depends only on the returns. So if we assume that all of the returns are the same, then the coexistence point in the center is the symmetric point, 1/3, 1/3, third. That would be the coexistence. So, so this is a sort of simplex plot. So these are proportions. So a plus b plus c equals 1. So it's not a three-dimensional variable system. It's just a two-dimensional variable system. So the standard way of representing that is in this triangle. The corners correspond to all playing strategy or population A, population B, population C. So these corners are the three fixed points. The center is the equilibrium, and it's unstable. In fact, you can prove it. So this is Chris Griffin, my collaborator. He proved the theorem, which appears in this paper, which is that the interior fixed point is always unstable, independent of the parameters. Whichever parameters you choose, coexistence is always unstable. There is always coexistence, which is nice, but it's always unstable. This is just a numerical plot of some of that, and then I thought it would be good to show numerics for the non-symmetric case. So this is just some arbitrary R1, RA, RB, and RC are just different values here. So the fixed point is not at 1/3, 1/3, 1/3. It's shifted off, but you perturb a little bit in any direction, and it eventually finds one of these three fixed points. Oh, that's the theorem. So, yes, so let's see. The following, so these are the assumptions, of course. For the theorem, you have to make certain assumptions about the different cases of the payoffs. In these cases, then, the interior fixed point is always unstable and is also a point of minimum population growth for the system. We are only looking at proportions. That's why three populations sum to 1. But then there is also the entire size of the population as a whole, which continues to grow. The coexistence is the minimal point of population growth. So it's interesting. Okay, and this just shows the basins of attraction. So for these sort of three species public good, the blue, the red, and the bright green here, let's say bright green, these are all the initial conditions that lead to the entire population playing strategy C. Everybody else is extinct, except for this population, which survives on its own because it has benefits from its one public good.
Excuse me, you said the
Yes, I'm
the
sorry.
total population is growing, right?
Yes.
So does that actually mean that one dies out, or just that its percent versus one?
It's in this case they do die out faster than the growth of them.
So it's not just that the percent goes to zero.
It's not just that the percent goes to it. They do die out, but there is still a growth rate of the population as a whole. But what's interesting, I mean, and this theorem, I'm not including the details here, but it's a very surprising result, possibly deep, but I can't tell you about it being deep. This, if you look at the growth rate of the population as a whole, U plus V plus W, that point is minimum at the coexistence point. I feel like there is a deeper theorem that would explain why that is true, but I do not know what that is. Okay, because even out here, these are let's pick some point here. This red region just means that this initial condition will lead to this fixed point. But the growth rate of the M, we call it M, the total population, here is larger than it is. So this is the minimum growth rate of the entire population. So I have a feeling that one of the talks I give, or someone who reads the paper, or eventually perhaps I'll figure it out, or Chris will figure it out, there's some reason why that is true. It can't just be coincidence, in my opinion. Okay, so for reasons that are, I guess, just Chris and I thinking about our interest in this game, there is no, I just want to emphasize, these are just equations that we are to some extent playing with. I do not have a physical system or a biological system in which I'm thinking about three public goods games that have this cyclic structure. Nonetheless, we sort of wondered, well, okay, now we've got a public goods situation with three different public goods, coexistence, but the coexistent point is unstable. What can we do to stabilize it? I just wanted it to, that question just comes from the idea that it would be interesting to know if 3 coexisting public goods games could be made to be stable. That was my requirements, or my idea. Can we do that? So Chris spent a lot of time, I spent a lot of time. We tried a number of things, and we eventually found something that stabilizes the coexistence, and it was somewhat surprising. Okay, so I just want to say the cyclic, so this just to make everything clear, the cyclic public goods model leads to the dominance of one product, one species with no cheaters. Because everyone's a cheater, but the other 2 games have disappeared, so it's just that one population producing everything, which is better, but the other games are not being played. It's a mono culture of one species. Is it possible to have all 3 populations coexisting and have that point be stable? So this is a different version of rewriting the model that we have. We have 3 populations that have this sort of replicator-like growth dynamic. These are, U dot is proportional. It's a birth process, proportional to UV and W. PA is the fitness. I didn't write it this way before, but now I'm writing it this way. These are the 3 fitnesses of the 3 games, and if you write it in terms of the proportions, UV and W, then you get the relative fitness. So it subtracts off the average. And that's something that, well, let me just say, that's something that everyone told me, yes, that's true. I couldn't, it's either very obvious, it took us a long time, I mean, it's not that long, but everyone seems to know that that's true. I couldn't find a reference for it, but I just want to point out the difference between these equations. This is actually U plus V plus W, time to write on the board. Are there smart pens that I can use?
Well,
Yeah,
turn the whole thing.
I have to turn it on.
Yeah.
Excuse me. Capital U plus capital V plus capital W is equal to the maximum. If I divide through by m, it's little u plus little v plus little w is equal to 1. I'll put it over here as well. So I just want to make a distinction between this is sort of the most natural way to write the model in terms of the actual numbers, and the sum of them is the population m. But if I divide through by m, I get little u plus little v plus little w is equal to 1. So if I take the equations that are now sitting in front of you, and I divide through by the sum, you see here's m right here, u plus v plus w, then I get a slightly different equation, and what's surprising is that you sort of get the fitness of each species minus the average fitness. So the actual populations are growing according to their fitness. The proportion populations are growing according to the relative fitness. Okay, these are how they turn out. We found that if we modified the dynamics by subtracting something from the fitness, so now we are modifying the actual equations are being changed. We artificially subtract fitness from every species. And we do so proportional to the population size. If you just subtract a constant, it doesn't do anything. If you do this, the interior fixed point is stable. You can see that it's stable by doing a linear stability analysis. That's sort of how we found it. And you can do it numerically. Actually, I don't remember, because we were both numerically simulating and trying to mathematically see what it would take. This is an imposed penalty. So what we're doing is we are imposing, okay, we're almost done.
Yep.
What does this mean? We're taxing. We're taxing the populations. And I can tell you why it distributes. Now I like to call it penalty. I don't like to call it taxation, because when you tax wealthy people, you do something with their money that benefits everyone. And that's not what we're doing here. We're simply punishing or penalizing populations if too many. This is a tax rate where the tax rate depends on the number of people in that tax bracket. That's not how it is.
So it's a death rate, right?
It's effectively a death. It's a nonlinear death rate. We're putting it here, so it's u squared. It's coming in as u squared. So it's a nonlinear death rate. That's right. So we're just penalizing the population. Yeah, it's just you could say it's a death rate, but it's a penalization. What this does is it mutes the growing attractiveness of any dominating population. So going back to this picture, if you start here, the reason you're pulled away is ultimately everyone becomes this population. But as you get closer to one population, the cost of playing that strategy is sort of increasingly punished as you approach it. So greater than some condition that depends on the return, you get attracting, or you can get centers. So that's basically the last thing we did here. And I'll just mention, we showed that there could not be a limit cycle because you can diffeomorphically, which is not surprising to you at all, you can diffeomorphically map this model to the rock, paper, scissors model in the replicator, which is known to not have limit cycles. So we know that we don't have limit cycles here as well. We either have attracting center or unstable center if beta is too small. Beta is the penalty rate here, or neutrally stable. Okay, that's the stability condition. All right, so since I'm out of time, I'll just put my summary here of the different models I've shown you here for public goods games, and I will take any questions. Thank you.
I'm going to slip in a quick one before I put it out to the audience. In stabilizing this fixed point,
yeah.
Do you go through a hot bifurcation? Because you've got
no.
two complex eigenvalues.
We have not. I haven't seen this.
Okay, but you've got a threshold on beta, which looks as though you might be getting those eigenvalues to cross the imaginary line.
Let's see.
Yeah,
This is a set. I don't. I mean, this is maybe I'm just not. So maybe this is a point that I missed. We go from this is stable, unstable through this, but I don't think we have a.
You don't get a you don't get a periodical.
No,
No.
that would be.
Okay.
But that would be the same as a. Yeah. So I don't think we see alpha. We didn't see it, but maybe we missed it. I did this one.
Be worth looking for.
Yeah, this one we didn't run through XPP, so I can't actually be sure, but I don't think so.
All right.
Thanks.
Questions? Yeah. No questions.
Michael, do you have any other questions?
No, you're making me think. Yeah. I mean, it looks as though you have some interesting dynamics from these figures. What's the top picture?
This is the spreading. Actually, since there aren't any questions, let me show you. The top picture is one of the frames of this movie. I didn't show you any of these movies, but let me show you this one. So this is a PDE simulation. This is one of the things we saw in the PDE. You start with a bump of cooperators that spread out, and they get followed by a bunch of defectors. Here, it'll just repeat. And so we just see this sort of pattern-forming system that happens. But what's interesting here is you see there is a Hopf bifurcation. And it's known in the PDE system that, well, in the ODE version of the PDE system, there's a Hopf bifurcation that occurs, so you get these weird traveling wave states. So I guess the one thing I would say about what we've done is, at the beginning I showed you a model which does not allow for coexistence. Everyone cheats, and then you have extinction. So we were inspired by the Christoph Howard and company's modification, right? Let's look at this group of size S. That's an attempt to patch the population and to try to fix it. So what I've shown you here, since there aren't any questions, I'm sort of summarizing my summary slide. What I've shown you here is 3 different ways to avoid everyone cheating and everyone going extinct. Space as a partial differential equation, as a sort of replicator diffusion system. Space in a more discrete way, where you have migration between nests coupled on some network. And in each case, you might look for possible applications in a case where either you have a continuous system or you have a discrete bunch of nests. And the third thing we showed is multiple public goods games. So what have we done? What have I just shown you that we've been spending all our time on? We've just increased the number of ways, mathematical ways, that we can see that a public goods game doesn't just lead to a disaster. We just added 3 more examples. We didn't. There was no phenomenon that we were trying to explain. We just added 3 more mathematical examples. Yep.
Have people looked at punishments for cheaters? In the microwave, everyone gets in a gang.
Yeah, right. People have looked. So there is a lot. There are a lot of games. Off the top of my head, I can't think of a punishment dynamic in public goods, but there's a lot of punishment dynamic. So there's a lot of altruistic punishment. Altruistic punishment. So I should say, in game theory or sort of game theory approaches, there's a list of things. I said at the beginning, why would you contribute to the public good? Why not be selfish? So cooperation, contribution to the public good, behaving fairly, and altruistic punishment, which is I take my own energy to shout at someone, even though I may never see them again, to correct them for what they just did. These are things that need to be included as add-ons into the current theory. So I'm pretty sure that there is the inclusion of punishment in some sort of public goods game. I just don't know what it is. Yes, sir.
In an actual biological system, though, you have a whole nested family of type of things. And you have a situation where you being the most fit within your little subgroup doesn't mean that you are the best thing for the overall population over a period of time, etc. So there's these competing fitness. Maybe you breed, having people that breed real good, it's actually kind of useful to have a major population drop.
Correct.
On the other hand, you want something to control it. And so there's lots of multiple games being played at multiple levels, which gets very complex.
Right. The problem is that as my understanding, I'm not an ecologist or a biologist, but my understanding is, you need more meta dynamics to select those. I mean, I can certainly understand why something that I observe biologically is useful, but how does that get selected for? Mechanic. I don't say mechanic.
Is selected for.
I'm sorry.
Diversity is selected for. It gives you robustness.
This is in
It's
a way
like,
this
it's like a
is
species. If they inbreed too much, they become very fragile because they don't have the robustness in the genome for that.
right. So I think that the mathematical understanding of exactly how diversity leads to robustness, the support of robustness is the thing that I think we need to understand more. How that arises.
Well, let's thank Henry